You ready?
Yeah, sure. Oh,
okay, let's get rolling. So
well.
our next speaker today is Jean-Emile Bourgine from CIMIS, and he's going to talk about free field representations of quantum groups in q-deformed W-algebras through cluster algebras.
Yes. Yes, thank you very much, Peter, for the introduction. Yes, so that's another cluster algebra talk, although I'm not going to insist much on this. So let me, of course, start by thanking the organizers for this wonderful conference. So indeed, today I'll talk about free field representations of quantum groups and q-deformed W-algebras. So that's going to be a very different style of talk from the previous one. No theorem, just ideas and pictures mostly. So this is a work in progress with Misha Bernstein here and Junichi Shiraishi. But part of the talk is actually based on earlier results obtained with Sebyok Jong back in 2019. So let me start with some very general motivation, although for today's audience, I probably don't need to convince you that quantum groups and W-algebras are maybe the most important algebraic structures in mathematical physics. But we're on TV, so maybe it's good to start with this. Right? So as most of you know, quantum groups enter in the construction of quantum integrable systems through the Hopf algebra structure. They provide solution of Young-Baxter equations, and this is used to derive exact results on these systems through techniques like algebraic Bethe-Ansatz, for instance. On the other hand, W-algebras describe symmetries of a class of quantum field theories in 2 dimensions with conformal symmetry, so they have a Virasoro subalgebra. These conformal field theories form the best understood type of quantum field theory thanks to the presence of these very large symmetry algebras. This is all very well known. And I guess also most of you know that in the 90s, an attempt was made to combine these 2 algebraic structures in the definition of q-deformed W-algebras. So this is trigonometric deformations, which means that the algebraic relations are no longer quadratic, very much like quantum groups. However, at this time, the Hopf algebra structure remained a bit of a mystery until very recently. So in 2009, Aldai, Gayotto, and Tachikawa proposed a correspondence between a class of 4-dimensional supersymmetric gauge theories, class S, as Misha was mentioning, and 2-dimensional conformal field theories. So this is known as the AGT correspondence. And mathematically, this correspondence implies a relation between free field representations of a quantum group, here the affine Youngian of GL1, and these Wn algebras with an extra free field. And actually, that's these extra free fields that give the coalgebraic structure. So in fact, the trigonometric deformation of the correspondence is easier to study. So in this case, it relates free field representation of the quantum toroidal GL1 algebra, so the algebra that Sasha was discussing at the beginning of his talk, at level n, 0, so you have n free field and bosons. And this is related to a q-deformed version of the Wn algebra that I mentioned before. So today I will be focusing on this q-deformed context. So what's the interest of this? Well, the main interest is that the presentation's theory of quantum groups is easier. Now, there's more than 6 folds, far more. Representation theory of quantum groups is easier than W-algebras, and this can be exploited to better understand them. And here, what we'd like to better understand is the definition of these q-deformed W-algebras. Very little is known for them. So all this is very well, but so far the correspondence has been established only for principal W-algebras. So first of type A, then type BCD, and also supersymmetric cases by Fengin, Jimbo, and Mukin. Now the question is, how about W-algebras associated to other choice of embedding? There is a whole zoo of W-algebras. So today I focus on type A. And for any embedding of SL2 in SLN, you can define a W-algebra through this Drinfeld-Sokolov quantum Hamiltonian reduction. Oh, that's too early. So if you take the trivial embedding, you don't reduce anything. So you start with this cat-Moody algebra, and then you have various reduction all the way to up to the principal W algebra that I mentioned before. In the q-deformed context, this is much less understood. That there's some work by Sebastianov, and this is expected to work the same, starting from quantum affine SLN and doing certain reduction. You're right. The question I would like to answer is, what is the relation between these non-principal W algebras and quantum groups? Right? So today I will be very modest and only consider the trivial embedding. So I will try to relate some free field representation of Wakimoto, the so-called Wakimoto representation of quantum affine SLN, to a toroidal quantum group representation in the same spirit as this AGT relation. And I will say only at the end of the talk a few words about the other embeddings. Now for this purpose, I need to consider a deformation of quantum toroidal SLN algebra, which we call the cyclically shifted algebra. So in my previous talks, I used to call it surface defect algebra, but Misha vetoed this, so no, it's a bit harder to pronounce, but I'll go by this. So where does this algebra come from? So for this, we need to do a bit of physics. So in this, that's true. So in this paper of 2019 with Sebior, we studied certain supersymmetric gauge theory in 5 dimensions that are defined on a particular space-time. That is written here. So you have the action of a discrete group, Zn, on the space-time, and you consider the quotient. And this action is just a rotation of the coordinates. This is labeled by 2 integers, nu1 and nu2, mod n. Now this particular context led us to introduce a new class of quantum toroidal algebras that play the same role as quantum toroidal GL1, but in this context of orbifolds. So they are deformed by these 2 integer parameters. So there are 2 particularly interesting cases. The first one that was actually already studied is nu1 equal 1, nu2 equal -1. This is known as ALE instanton. And this is associated to the undeformed quantum toroidal SLN algebra. And so in our work, we wanted to generalize this for arbitrary nu1, nu2. And another important case is nu2 equals 0, nu1 equal 1, which can be interpreted as the introduction of a surface defect. And this gives a new deformation of quantum toroidal SLN, which is the one that we need to consider for the connection with W algebras. So this can be interpreted as a cyclic shift in the Drinfeld double construction. I will explain this later. Okay. Yes, so that's the one we need for today's problem. Just to say a little more about this work, so with Sebiok, we wanted to generalize the Awata-Feigin-Shiraishi vertex operator construction for topological string amplitudes, or 5D Nekrasov functions. In this way, we obtain an algebraic construction of Nekrasov partition functions and also objects called QQ characters in this context of presence of surface defect. And this construction is actually relevant to a number of interesting problems, like the beta gauge correspondence, Q-Panové equations. I know some of you are interested in this, or this non-stationary Rossner wave function. That is some kind of deformation of McDonald symmetric functions. But that's a different story. I'm happy to talk about this during the break, but today I'll focus on W algebras. So that's the outline of my talk. Now, in this particular instance, the correspondence is a bit confusing because on both sides you have quantum groups. So I'll still refer to one side as W-algebra side and the other one as quantum group side to somehow keep track of things. Now, for simplicity, I'll start with the finite case, which is better understood too. So this is in the sense of finite W-algebra. So the W-algebra side will be finite quantum group UQSLN, and the quantum group side will be this deformation of quantum affine SLN. And then I'll move to affine case. W-algebra will be quantum affine SLN, and the quantum group side will be this deformation of quantum toroidal SLN. So let's start with the W-algebra side. So this is the recalling the definition of the finite quantum group UQSLN generated by E, F, and K. Indices I running from 1 to n minus 1. So these are the relations. The last two relations are the Serre relations. I can show them. Q is the quantum group parameter. Beta is the Cartan matrix. You have a q-deformed commutator. So for this, I want to consider the so-called Heisenberg representation that has been introduced by Awata, Normi, and Odake in '93. That is defined using n(n-1/2) pairs of quantum torus variables. So these are q-commuting variables, and they are indexed here by lower triangular matrices. So this is how the representation look like, and well, it's already a little bit complicated, and this is going to be much worse in the affine case. So yes,
correct me if I'm wrong. So if I remember correctly, if you just have a theory on the defect, that gives you this finite W algebra, so quotient by some kind of Virasoro constraint, right? So full W algebra, you had this. So the toroidal case that I'm talking about is from the defect theory, not from the full.
You need an orbifold to get toroidal SLN.
Yeah, but and then you take the limit when you stay on the defect, right? So you're gonna get.
No,
this.
I don't take any limit. I consider
then
the.
Then I have the instanton parameter. It will be like elliptic algebra, right? What's the meaning of Yang-Mills coupling in your algebra?
Yang-Mills coupling is yeah. I can show you later. It's not really relevant for this talk. It's not going to appear here. It's come from this vertex operator construction of Awata, Fegin, Shiraishi. You need to glue them in a certain way.
Yeah, but then there should be some kind of Virasoro constraint in place, right? So it's not the full full-fledged W algebra. It's going to some kind of reduction, right?
Not with what I have in mind. Maybe we have different things in mind. Yes. But with this construction, we get honest W algebras, no reduction. You'll see. Right. So, where was I? So yes. So we have a complicated expression, but inspired by the work of Schrader and Shapiro, we can actually rewrite this complicated expression, write them in a simpler form. And for this, I need to introduce this telescopic sums. That is just so the sum. So this is the function of this argument y1 to yn that are non-commutative variables will be just y1 plus the product y1, y2, and so on all the way to the full product. There is a normal ordering we should take, but I'm going to skip these technical details. So with this, we can write the generators in this form. Right? So that's already slightly simpler, at least for E. For F, it's still a bit complicated. So this is written in terms of this sum or just product for the K generators. And this involves these monomials Y that are, you see, monomials in terms of the X and Q theta variables. But there's still a lot of hidden structure, and this can be encoded in a quiver or a seed in the cluster algebra language. So what we do is we, to each node of the quiver, we associate one of these monomials. Right? And the arrows of the quiver will encode the commutation relations between the various monomials. So we'll have two types of arrows here. The plain arrows, where the q commute with a q square, and dashed arrows. So that will be only between frozen nodes. that have only a single q. So examining the q commutation relation between the monomials, we can draw a certain quiver. I will show it in the next slide. We call this Kashi-Kojima quiver. That's a reference to the island on which this type of representation were introduced during some conference. Maybe one day there will be a BIMSA quiver, who knows. So then from the quiver, we obtain the generators following paths between two frozen nodes. For a path, we can obtain, we have a sequence of monomials, and we can define the telescopic sum. This will give us the generators E or F, depending on the path. And we can define the product of monomial. This will be for the K generators. So here are the example for n equal to 3, 4. So this is UQSL2. You have 4 nodes, 2 frozen, 2 unfrozen. And the E generators is obtained from the path going from Y11 to Y13, the horizontal path with black arrows. And the F is the other path following the blue arrows. This is SL3. So here this gets a bit more complicated. The E1 is obtained following the first black horizontal path. E2, that's the second pass. Yeah, I have to be very slow and gentle. And F is a bit more complicated. You follow the blue arrows. I see why. So for instance, F1 will be Y13, Y10. So here I doubled this node, so you have to identify nodes with the same label. This is to draw things in a better way. So Y10, then you go to Y22, Y23, Y11. That's the path for F1. F2 is something similar. And this is SL4. As you can see, it starts to look a bit like a sailing boat, which is very appropriate for an island. So that's all for my W-algebra side. Now let's move to a quantum group. So on this side, we introduce some deformation of quantum affine SLN by this parameter C, that is an integer mod n. So this is generated by, just like quantum affine SLN, E, F, K plus K minus. So it's more like a deformation of the Drinfeld double. And they are now indexed by the nodes of the affine linking diagram. So this has the cyclic 1, 2. So this is this index omega here. So you see in this relation some shift of indices by C here and there. Right, I'll come back to this later. I have omitted cell relations because they are not deformed. So this has a shifted Hopf algebra structure. So it's very similar to the shifted quantum group construction, for those who know. So you have a coproduct that is homomorphism between the algebra and the tensor product of 2 copies with different parameters C's, such that you have this linear relation here. So this is the coproduct. It has the usual form with, again, a couple of deformation shift by C here and there. So a couple of things to notice. So we cannot impose this relation K plus K minus equal 1 here because they no longer commute. So unless C equals 0. When C is 0 mod n, we recover actually the algebraic relation of quantum affine SLN, mod this relation. We can actually construct it as a Drinfeld double with a twist by an abelian group. So it's very similar to a shifted quantum group again, but with a different type of automorphism. This is the one that just rotates the quiver here. So this is why if you look at the relation inside the Borel subalgebra are not deformed. So if you look at K minus E or K plus F, you see there is no deformation, but the commutator EF, for instance, or K minus F are deformation. All right, so that's the definition. Now what's the main idea here? Right? So in the next slide, I will define a representation with C equal 1. And then what I want to do is take n minus 1 times the coproduct and evaluate in a tensor product of C equal 1 representation. Since it's additive, I get a C equal 1 representation. But this is now 0 mod n, so this is actually a representation of quantum affine SLN, undeformed. And if I look at the subalgebra, the vertical subalgebra, so I just forget the generators associated to the node 0, then I get a finite UQSLN subalgebra. And this is the one that I will compare with the W-algebra side. So let's define this. So C equal 1 representation. We have n pairs of quantum torus variables that Q commute, it's a bit different here. So this involves a Kronecker delta mod n, and that's the form of the generators. As you can see, they are, again, monomial in this quantum torus variable. Now, taking m minus 1 coproduct, we find a representation with C equal m, with n times m quantum torus pair. Generators have this form, so E and F are, again, telescopic sum, and K's are just product of these monomials. And I can do the Schroeder-Shapiro trick and code everything in terms of quiver, and I end up with this rectangular quiver. It's a very nice structure. So you'll notice the periodicity in the horizontal direction. That is just the cyclicity of this linking diagram that you see here. And the vertical direction corresponds to the action of the coproduct, so that's why you see the same type of cells that repeats themselves. So if you follow the blue arrow, you will get the E generators. If you follow the red arrows, you will get the F generators. So that's good. Now we need to compare this with W-algebra. So for this, I will restrict myself to SL3. I'll start with the rectangular quiver, and since I only look at a certain subalgebra, I can remove two frozen nodes that only appear in these generators. I end up with this quiver, so I've rotated it by 90 degrees to make the comparison easier, and I replace the periodicity by doubling this x01, x02 nodes. So this doesn't look quite like Kashiko-Jima yet, but we also have another kind of technical issue, that we have too many quantum torus pairs. Right? So in Heisenberg, we have n minus 1 over 2. Here we have n squared. Right? So we need to eliminate n plus 1 over 2, and we can do this with Casimir. So it's a bit of a technical remark. So what happens if you take a representation of this quantum torus, for instance, on Lorentz series of X, you will see that the representation is highly reducible, and you use this Casimir to label the sub-representations, basically. So once you've done this, you can actually compare the quiver. They don't look the same, but they're actually equivalent under this mutation at X11. Yes, I used to show this directly with my laptop, but today I won't have time. So just trust me that they are mutation equivalent. All right, and so if you compare generators in the new variable, we find that the two representations are indeed the same. There's actually a bit of a bonus. You don't really have to remove these two frozen nodes. You can keep them, do the mutation, and what you get is, well, something that looks a bit like, so this is a deformation of Kashiko-Jima with this extra red node, and this is actually the evaluation representation of quantum affine SLN. So you have the same number of quantum torus variable, but one more Casimir, one more commutative variable that is the spectral parameter. Okay. So that's the finite case. Is there any question? So let me move to the affine case, which work pretty much in the same way, thanks to Misha's brilliant idea of Kiraization of the quantum cluster algebras. So let's see how this works. So on the W-algebra side, now we have the Drinfeld presentation of quantum affine SLN, so the same algebra as before, but a different presentation. So instead of having these extra generators associated to the node 0, now you have this current, but the label is from 1 to n minus 1. So roughly speaking, x plus, x minus are E and F. Psi plus, minus are the case. So the free field or Wakimoto representation of this algebra has been derived in this paper of Awata, Odaki, Shiraishi. So let's have a look. That's what they got. So that, I should say, it's very complicated. So this involves n squared minus 1 free fields, A, B, and C. Q-deformed vertex operators, half vertex operators, and so on. It actually goes on a little bit on the next page, but I'm going to spare you that. But we can use Misha's idea to make sense of all this. So Misha's idea is to replace these quantum torus variables by vertex operators. So to each node of the quiver, now you have a vertex operators. You distinguish unfrozen and frozen nodes of type plus and minus, depending on the self-OPE of these vertex operators. So this can be encoded using this rational function, phi n. That's a shortcut notation for OPEs that I use frequently. So this double dot, it just means that you have this normal ordering. Right. And the arrows between these nodes will encode the OPEs between different vertex operators. So you have three types of arrows. This is written here. Remarkably, everything is expressed in terms of this function phi. So the main new things here is that now the arrows carries a label alpha that you see enters in these OPEs. So in this way, you get, again, relatively simple formula in terms of telescopic sums. Now the complexity is that you have to shift the argument according to labels of the arrows, but I'm going to skip this. And you do the same tricks, and you end up with Kashigoshima quiver, right, with some decoration on the arrows. So this is SR3. You can do this for any rank. So now let's move to quantum group side. So on this side, we introduce this deformation of quantum toroidal SLN. So now we have Drinfeld. First I define the structure function. So it's this function. So depends on two quantum group parameters, Q1, Q2. But just like in Misha's talk, it's useful to introduce Q3 such that the product is 1. So this is what plays the role of the Cartan matrix in the Drinfeld presentation. This structure function. So the algebra is defined in terms of this Drinfeld current, now indexed by the whole affine linking diagram. Right? And these are the relations. So again, it looks very much like quantum toroidal SLN, but you have this shift of C in the indices that actually this time comes together with a shift of the argument, as you can see, for instance, in the x plus x minus commutator. Again, it's a shifted Hopf algebra with a Drinfeld coproduct deformed accordingly. And so when C is 0 mod n, we recover quantum toroidal SLN. We have also a GLN version for those who are curious about GLN. This product turned out to be central, which is quite interesting. And we have, again, a Drinfeld double construction, but now you also have to shift the argument.
Is it different from that elliptic algebra by Fagin, Schreis, and others?
I think so.
It's different.
I think so. No, I don't think this had happened before. I mean, we looked for it. And, there is some kind of equivalence, we believe, with the Negut's kind of algebra defined using shuffle algebra. So some, yes, we can talk later. Yes. Right. So and the zero modes here define a shifted, so cyclically shifted quantum affine SLN subalgebra. This horizontal subalgebra. Again, same trick. I defined a C=1 representation. So now this is going to act on a Fock module. built using N boson. So this is the standard construction. You start with a vacuum state that is annihilated by the positive modes of Heisenberg algebra, and then you define this charge vacua and act with negative modes to build the states. Pretty standard. And then, so this in this horizontal representation, so it has level c equal 1. It will depend on n complex weight that I call u, and integer weight n. But to simplify, actually, the formula next slide, I just took u equal 1, n equals 0. That's going to be enough. So here are the expression of the generators. So this Dunfer current are just deformed vertex operators. So it's a sort of deformation of the representation of Naivan and Frankel obtained a long time ago. Right. So yeah, note that the algebra of zero modes corresponds to the previous equal 1 representation. And when you take n equal 1, you end up with the horizontal Fock representation of quantum toroidal GL1. Okay. So this is the same story. We take m minus 1 times the coproduct. We find representation with c equal m. When m equal n, the deformation parameter disappears from the relations. And you obtain representation of quantum toroidal SLN. We remove the generators with omega equals 0 and get quantum affine SLN. All right. So this again rectangular quiver, and by the same type of mutation as in the finite case, we relate this to Kashikojima. Okay. To conclude this section, let me also mention the original AGT case. So this is the case n equal 1. In this case, you have only one node, so the shift disappears, right? And we end up with quantum toroidal GL1 at level m, 0 after m coproduct. And our rectangular quiver degenerates into this, right? So this is indeed the quiver that is associated to a principal q-deformed W-algebras. Just a bit of comment. So previously we had nodes without any loop. And this corresponds to fermionic screening. But in this case, loops appear, so we now have this bosonic screening. We'll have two screening charges associated to this, and elliptic self-OP between screening current. Right? So this distinction actually also appeared in Fegin, Jimbo, Mukin, Wilkowicki when they built this W-algebra principle of SLM/N. So this relates a bit to their work. Okay. So I don't know, I should have like 10 minutes maybe? Or?
Yeah, like 12.
12, oh, wow, plenty. All right. Any questions then maybe?
So you have this infinite quivers for the finite case?
No, all the quivers are finite. No, the affinization or curarization is done by replacing this quantum torus variable by vertex operators. Yeah, so that's how it becomes.
You do have mutations?
We do have mutations, so we can define it. Misha actually defined this. You can, yeah. I mean, I don't want to show this, but you can define mutation. You actually use the R matrix of quantum toroidal GL1 to define this kind of mutation. Yes. Yeah.
Do you have some parameters related to your algebra?
Yes, I'll come to this the conclusion. You have maybe. Okay, I think I know what you have in mind, but I'll comment on this. I think this is a very good point. But actually, yes, exactly. Yes, and I do want it too. yeah. Let's come back to it. Okay, well, no, I have only 10 minutes left. All right, so let's summarize. So to summarize what we did, we oscillator representation of UQSLN and free-field representation of quantum affine SLN in the form of telescopic sum associated to pass in the Kashikojima quiver. introduce this cyclic shift deformation of quantum affine and quantum toroidal SLN algebra. I'm reading my slides if you're in front. We define quantum torus and free field representation for this new algebra, so for C equal 1. Construct new representation of quantum affine SLN, quantum toroidal SLN using the coproduct, and these are associated to the rectangular quiver. Restricting ourselves to the generators without the node 0, we find new representation of the subalgebra. And smooth transition. Are we still on TV? And so we relate the two representations using quiver mutation that we can define on the vertex operator in a certain way. Okay. Now, there are many open questions. For me, one of the most interesting one is, okay, so we have these rectangular quivers, n times m. We recover q-deformed W-algebras associated to trivial embedding when n equal m, and the one for the principal embedding when n equal 1 and arbitrary. Now, what happens in between when m is not equal to n? And is this somehow related to free-field representation of non-principal W-algebras? Can we try to understand the q-deformed Drinfeld-Sokolov reduction in this context? So, well, this is very much a work in progress with Ethan Fussman, a student at the University of Melbourne. We start to understand this a bit for SL2, but I'll try to convince you that this is the correct framework to answer this kind of question, just using some pictures. So let's start with quantum affine SL2, and there's actually another realization, another representation that you can obtain using a mutation on the quiver. So it takes this form. So it has two advantages. First, you now have a bosonic nodes, just like you have for a q-V-Razaro algebra. And your E is now a single vertex operator because you have this direct path between the two nodes. And this is the starting point when you do quantum Drinfeld-Sokolov reduction. Right. So the trade-off is, of course, that the F generators is much more complicated. But you see that if you can eliminate the free fields associated to the top of the quiver, and in the process freeze this node Y12 here, you end up with basically this part of the q-V-Razaro. And the extra node is actually not really important here. It's associated to the extra U1 factor that we don't really need. So we get q-V-Razaro from this procedure. We can do this actually fairly explicitly and derive some expression of this form that should remind you of Drinfeld-Sokolov reduction. So you have different vertex operator, but you relate q-V-Razaro stress energy tensor to x minus using some kind of relation like this, where A and B commute with this. So that looks very much like it. So, okay, you'll tell me SL2 is maybe a bit too easy. So let's move to SL3. SL3 is more complicated. But if we play around with mutation, we end up with the following quiver on the left for quantum affine SL3. That looks not so pretty. But I want to compare it with the 2 times 3 rectangular quiver on the right. And what we notice is that if we somehow remove the top, right, remove the top part and freeze Y12 and Y11, we actually recover this part of this quiver. And the extra node here corresponds to choosing a subalgebra of this part, so we can remove this extra frozen nodes. Perfect. Right, so somehow this can be embedded in the other one if we do things properly. Next, let's compare 2 times 3 after, again, a number of mutation with the quiver that corresponds to q-deformed Belavin-Kolyakov algebra. So this was, the representation was found by Harada using corner vertex operator algebra. You can encode in the same way this in a quiver. Oh, Bershetsky, yes, you're right. Thanks, Misha. Yeah, it was late yesterday night. Shutsky, Polyakov. Yes, very, very, very true. Okay. So if you focus on x01 that you freeze, you can identify it with x5, and x00 will become this x1 minus here. So again, you can somehow relate the two quivers, removing some frozen nodes, which means removing some free field. And finally, BP, QBP with principal q-W3. So this is very much like for SL2, you see. If you remove the two frozen ones and freeze x4, you'll end up with this part of this quiver here. So there's still many points to understand. It's just very preliminary, but so this, for instance, there's some transformation by Sebastianov that play a very important role here. But hopefully I convince you that this framework looks very promising to understand general q-deformed W-algebras. More open question, and I'll come maybe to this question. So we can consider BC type, this kind of comodular construction also, possibly. There should be also a nice application to beta gauge correspondence because the surface defect plays an important role in derivation of Hamiltonians and construction of eigenfunctions and all sorts of nice problem. So this should be the proper algebraic framework to study this correspondence. There's also connection with symmetric function with these GK-law representations. So one of the questions is what would be the analog of Macdonald polynomials of quantum toroidal GL1 in this deformed context? There should be also something like a Riesz-Macdonald, but yes. Is there an analog of Mickey's automorphism? So in physics language, this would be some fiber-based duality in the presence of surface defect. And finally, I think maybe that was your question. So next to the coffee room, there is a very nice poster that explains how you can obtain the tetrahedron R matrix, so this 3D generalization of Young-Baxter equation, using cluster algebras and cluster mutation. Right? So can we parallelize all this? Right? Can we replace the quantum torus variable that they're used in their construction by vertex operators and derive tetrahedron R matrix with a spectral parameter? I think that is possible, but yeah, that'll be nice to discuss this. And yes, and there might be also a connection with this q-deformed integrable hierarchies that we introduced with Sasha some time ago. All right, thank you very much.
Okay. Thank you. Questions?
So you showed the unpleasant free federalization of quantum affine SLN. So one of the motivations for them going to those efforts was that they wanted to construct free federalizations of vertex operators a la Franco-Rashitikin. Do you know if your simplification also works for those objects?
Yes, yes, yes. So yes, so the one with Drinfeld coproduct are much easier to construct, and we actually constructed them with Sebiok in our paper. So this is what I was referring as Awata-Fegin-Shiraishi construction. So yes, so we can just specialize the construction where we change a bit of things. So we will actually rewrite them and present them in the paper in a more cleaner form, maybe. But yes, yes, it's possible.
Oh, very interesting. Regarding the integral hierarchies, did you find a Lax pair for those hierarchies?
Not yet, no. So it's we're still trying to understand this thing. What we managed to do is deform this Jimbo-Miwa vertex operator construction, obtain Hirota bilinear equation and deformation. And from there, derive the equation of the hierarchies. But this depends very much on the coproduct because now the algebra is no longer linear. Right? It's a quantum group, so the coproduct is non-trivial. And this brings a lot of complications. So yes, but that's one of the to-do lists. I think it's a difficult question, but an interesting one. So probably sometimes we can propose something.
All right. Thank you.
Yeah, can we have any information of the intertwiners between Wakimoto modules from this cluster realization?
I think that's more or less the same as Robert's question. Yes, these vertex operators are intertwiners. Yes, we obtain them with Sebiok.
Yeah, but do we need any requirement for this Q? I mean, this Q and T for this validity of the intertwiners?
Sorry, I didn't get.
Do we need any specific values of the Q and T? I mean,
No. These remain arbitrary. You have just like for Awata Fegin Shiarishi, a constraint on the weight and on the levels. But yeah, it's very similar to that. It works surprisingly well, I should say. Yes.
Okay. Yeah. Thanks.
More questions? So you mentioned in passing about Arith McDonald polynomials. Like, is this a guess, or you actually think they will work? So, like,
no, it's very much question with asking yourself if you have anything relevant to say.
There was some work by Virginia Tech group, like Daniel Orr and Mark Shimazona. They had some geometric construction about Arith McDonald polynomials, so that could be related.
Yeah, so my personal guess, I don't want to speak for the other, is that so you have two types of Riesz-McDonald polynomials that corresponds to different coloring of partitions. Right? So one is like diagonal stripes, and the other one is like a zebra kind of thing, right? The vertical stripes. So the vertical representation, so the C equals 0 representation that is relevant in this intertwiner context, is the one that corresponds to this vertical stripe. That's surface defect one. And so if we have some sort of Mickey homomorphism or some relation between vertical and horizontal, so C equals 0, C equals 1 representation, which is still something we absolutely don't understand, then this type of Riesz-McDonald should play a role. Yes.
Yeah, that's very good.
But yeah, it's a bit of speculation at this time.
More questions?
I have something relevant to say. Okay, if I may. So what something I didn't explain, but I find quite interesting, is that you have also this kind of GK-law representations that you can define. So these are like tensor product of vector representation, for those who know. And this Junfeld, this x plus x minus current, they act a bit like McDonald operators, something. So you can define this kind of GK-law representation. These are C equals 0 representations, so there is no cyclic deformation. But you can take some limit of infinitely many variables. And what you end up with, in this case, is the one with the shift. So the C equal 1 representation, cyclically shifted. So that's maybe another approach.
It's like this deformation kind of emerges
from GK-law, yeah. I think that's interesting.
Okay, no more? Great, so back at 11:35, 6 minutes.